force convection. Under this video, okay, in this video, you will be teach on general thermal analysis for the internal force convection. So in the absence of any work interactions, the conservation of energy equation for the steady flow of a fluid in a tube can be expressed as Q dot equal to M dot Cp T exit minus T inlet. So M dot here represent mass flow rate. Cp is specific heat capacity. Te is mean temperature at exit of the system, and Ti is a mean temperature at inlet. Why mean temperature? We know that when there is a flow in a pipe, so I draw here, we have a flow in a pipe, so we have a temperature profile for the fluids inside the circular pipe. So let's say this is T inlet, and we have another temperature here is T exit. Just like velocity, we do not represent each of these layer in our calculation. We do not calculate each of the layer to represent the T inlet and T exit for these kinds of flow. Okay, so this is part N. We are not calculating one by one of the fluid layer. So what do is we are trying to find the mean temperature of all these fluid layer. Then we can only have one mean temperature for this flow. So if we calculate the mean temperature, and then we will get one temperature which is Ti, and for the T exit we will get another one temperature which is T exit. So T inlet and T exit is a mean temperature for inlet and exit. So Ti represents T inlet, mean temperature at inlet, and Te is a mean temperature at exit or outlet from the system. If we can compare with this system, so we can see that this Ti from the inlet, here is the point where we calculate for the T inlet, and then this is the point where we get the value of the T exit. So this is the same as what I draw here, that the Ti is a mean temperature at inlet and Te is a mean temperature at exit. So the thermal conditions at the surface can usually be approximated as I mentioned before, we have two conditions in the internal force convection. One is a constant surface temperature. So here we have T as constant. And another one, we have Q dot S. So this is heat flux, is constant. So we have two conditions in order for us to determine or to calculate or to do thermal analysis for the internal force convection. Okay, the mean fluid temperature must change during heating or cooling. Okay, either T as constant or Q as constant at the surface of the tube, but not both. So for these two conditions, only one can be occur at one time. It will not there would be no condition, there will be both of these conditions will not come together. It will be that question is for constant surface temperature or for constant surface heat flux. So it cannot occur simultaneously. it will be either constant surface temperature or constant surface heat flux. Okay, so for a constant surface heat flux, so the rate of heat transfer can be also expressed as, so here, to get the rate of heat transfer from the heat flux. So we know that this is the case of heat flux, constant heat flux. So we have these kinds of value. Okay, so we want to find what is the rate of heat transfer from the heat flux. So we know that the heat flux, we know that the rate of heat transfer unit is watt, whereas for the Q dot is watt per second. So, and then also not watt per second, watt per meter square. To remove meter square, we have to multiply with meter square. So here, meter square is the area. What area? We have to calculate the surface area. So AS here is not cross-sectional area. So you have to remember this. This is surface area. For the surface area for the cylinder is pi dl. So you must remember this equation and memorize this equation. And you have to remember that when you want to find what is the rate of heat transfer for the cylinder, you have to use AS, since the heat transfer occurs at the surface of the cylinder. Then we know that the Q dot S, AS is equal to Q dot. Then we can equate this equation with this equation here. M dot Cp Te minus Ti is Q dot. Therefore, we can equate M dot Cp Te minus Ti equal to Q dot As. Okay? So the mean fluid temperature at the tube exit becomes, so from here, we can rearrange this equation and we want to find what is the mean fluid temperature. So normally, the mean fluid temperature will not be given in the question since we have this constant heat flux. Therefore, it is your job to plug in all the values inside the question in order for you to determine what is the mean fluid temperature or T exit for the tubes, okay, or for the pipes. How to calculate? You have to use this equation. This equation comes from this equation. You just rearrange this equation, therefore you will get this. So you substitute Ti and Q dot S is heat flux, and then As is surface area, M dot is mass flow rate, and then Cp is specific heat capacity. Okay, the surface temperature in the case of constant surface heat flux can be determined from, so we know that this is internal force convection. So for the convection process, the equation for convection is Q dot. We know that the heat transfer for rate of heat transfer for the convection process is H As. So let's say the heat transfer is from surface temperature minus Tmin. Okay, this is Tm is Tmin, T exit or T inlet. Both of them are the same. We call it as a mean temperature. So now we have a constant surface heat flux. We rearrange the As. We must bring it to the left hand side. So we will get the Q dot over As is equal to H Ts minus Tm. So from here, Q dot over As is rate of heat flux. So Q dot equal to H Ts minus Tm. So this is where this equation comes from. Okay, from the rate of heat transfer for the convection process. So from here, we rearrange and then we will get that Q dot S heat flux is equal to H Ts minus Tm. So we rearrange in order for us to find what is the Ts. Ts equal to Tm plus Q dot over H. You must remember that this Ts is actually the surface temperature for the fluid, for the cylinder. Sorry, Ts is the T surface at inlet. So now we deals with internal force convection. So we know that the tubes will have thickness, okay? And sometimes we can assume that the thickness is negligible, and that is when you learn in heat exchanger. But now for the thickness, we have the cylinder with a thickness of 3 centimeter, for example. So this Ts is represent the temperature inside, the surface temperature inside. So we are actually calculating the temperature at this point. We are not calculating the temperature at this surface temperature. Okay, so sometimes you might confusing that this calculation is for the surface temperature at the outside of the cylinder. Okay, so you must remember that Ts from this equation is for inlet surface temperature. Okay, so Tm in that question represent for the mean fluid temperature. You may use either T inlet or T exit. Both of them are mean fluid temperature. Okay, so Tm can be T inlet or T exit. So T inlet or T exit. So you may use both either one to substitute into this equation. Okay, and maybe you may use that Tm for T exit. Okay, because we want to find the rate of heat transfer, and normally Tm is Tm is mean fluid temperature, and it can be either Ti or Te. Okay, we move to this. In the fully developed region, the surface temperature Ts will also increase linearly in the flow direction. So when we applying the steady flow energy balance to a tube slice of thickness dx, so here you can refer to this figure. Okay, we are taking a tube slice with a thickness of dx here. So the slope of the mean fluid temperature Tm can be determined. So here we have Tm at the inlet. Here is Tm, and then this is the exit for this boundary system lah. Okay, so we have Tm and Tm plus dTm. So change of temperature, mean temperature. So from here Tm can be determined from this equation, m dot Cp dTm equal to Q dot S P dx. So we know that this is actually constant. So dTm over dx equal to Q dot P over m dot Cp is constant. So we're noting that both the heat flux and H are constant. So we have this equation. So dTm over dx equal to dTs over dx. Then in the fully developed region, so we know that for the fluid flows in the pipe, there will be two regions. One is hydrodynamic entrance region. Second is hydrodynamically fully developed region. So this is the region where fully developed region where we want to um, what to derive the equation for fully developed region. So at the fully developed region, we know that Ts minus Tm is constant. Okay, so after combining the equation, we get this equation 822. So after combining those three equations, we will get that dt over dx, dts over dx equal to dtm over dx equal to q dot sp over m dot cp is constant. And for circular tube, dt over dx equal to dts over dx equal to dtm over dx equal to 2q dot s over rho vat average. CPR is constant. Okay. So from here, we can see that it can conclude that the change of temperature per x is constant for the fully developed region. So you may see from this figure, so this is entrance region where there will be a change in the temperature, and at this point the delta T will be change as it increase uh, the x as the x coordinate increase until to the point where the fully developed region starts. And at that point where the fully developed region starts, we can see that the delta T here, so we have delta T, is the same as as the x increases. So this is where that equation, that derivation is actually tells us. So for the region, for the fully developed region, change of temperature over x is the same until L length of the fluid. L length of the tubes. So at this point here, fully developed region, you can see that this is the fully developed region. You may see that the delta T will be constant throughout the x. As the x increase in the fully developed region, the changes or the delta T here is the same for from the inlet temperature from the start of the fully developed region up to L length, L of the cylinder or tubes or pipes or whatever things that is in circular shape. Okay. So for a constant surface temperature, so that is for the constant surface heat flux. For constant surface temperature, here we have energy balance on differential control volume. So we have this equation. Since the mean temperature of the fluid Tm increases in the flow direction, the heat flux decay with x. So from here, the surface temperature is constant, and we have this change of temperature, mean temperature equal to negative d Ts minus Tm, because the temperature, surface temperature is constant, and then the mean temperature of the fluid increases, then we have these kinds of equation, and we have dAs equal to P dx. Therefore, this equation becomes like this. Okay, d Ts minus Tm, Ts minus Tm equal to negative Hp over m dot Cp dx. So we, after all this equation, we integrate and we will get that we integrate and then we get that ln Ts minus Te equal over Ts minus Ti equal to negative Has over m dot Cp. So this is the equation derived from this equation. Okay, so we get this. So by taking the exponential of both sides and solving for TE, so we are concerning on the TE value for the constant surface heat flux, constant surface temperature. Then we have the exponential to remove the ln of this equation. So we will get that TE, in order for you to determine the exit temperature for a constant surface temperature, you have to use this equation. So TE equal to TS minus TI exponential negative HPL over m dot Cp. I believe that you already see this equation previously in the external flow convection in the tube bands, where we want to find what is the TE. Okay, so this is the equation that will be used by us in order to determine what is the exit temperature for a constant surface temperature. So H is heat transfer coefficient, and P is weighted parameter, L is length, then m dot is mass flow rate, Cp is specific heat capacity. So here I would like to explain about P times with L. So here P is a weighted parameter, times with the L, we will get this is surface area. So P times with L is weighted parameter times with the length, and we will get surface area. So in other words, PL can be changed into pi dl. So di. Okay, you can calculate what is the surface area of that cylinder or tubes or pipes. Okay, the temperature difference between the fluid and the surface decay exponentially in the flow direction, and the rate of decay depends on the magnitude of the exponent. So the decay of here, the decay exponentially in the flow direction, and it depends on this equation. As we can see here, this exit temperature exponentially depends on this. So this is same as this one. So HAS over m dot Cp. And this dimensionless parameter is called the number of transfer units. So this is what we call as an NTU. Okay, large NTU value, increasing tube length marginally increases heat transfer length. Heat transfer rate. And small NTU value, heat transfer increases significantly with increasing tube length. Okay, so that is two types of value lah. If you get large, what will happen? And if you get small, this is heat transfer is increases significantly. So at this point, you may see that with a small NTU, you may achieve you may increase your heat transfer significantly. Okay, and then from here, solving the 829 equation 829, here we have T exit here. So we are solving this, and last we will get that we substitute into this equation Q dot equal to, first we solve 829 for MCP gives the value of this, okay, this equation, sorry, not value, but this equation. And then after you get this equation, you substitute into this equation. So you want to find what is the Q dot. So m dot Cp delta T actually. So here m dot Cp equal to HAS delta T ln. Okay, so you will get this delta T ln. Delta T ln, it is the same as before, where this delta T is actually delta T ln is delta T log mean temperature difference. So you have to remember this equation. For a constant surface temperature, so you want to find what is the rate of heat transfer, you have to use this equation, the log mean temperature difference. So first you have to determine what is the T exit and then substitute into this equation to find what is the delta T log mean before you substitute into the Q dot. So that is how you calculate for the constant surface temperature. So for a constant surface heat flux, now I will explain about the Nusselt number for a constant surface heat flux. And for a constant surface heat flux, the Nusselt number is constant for which is equal to 4.36. So for fully developed laminar flow in a circular tube subjected to constant surface heat flux, okay, the Nusselt number is also a constant. Is also constant with a value of 4.36. Okay, so you do not have to worry when you deal with a constant surface heat flux. You want to find what is the H, so you just equate a HT over K equal to 4.36. Okay, the constant surface heat flux, for example, you have radiation, that is constant surface heat flux. Or electrical heater, okay, that supply energy to your tubes. Okay, next, this under constant surface temperature, we have laminar and turbulent flow. So we have to use a proper equation in order for you to determine what is the Nusselt number for both cases. So first, for the laminar flow, we have laminar and entry region. So now for a laminar flow, the Nusselt number is 3.66 for a laminar flow. Okay, means that for a flow in your pipes with a Reynolds number that below than 2,300, it will be a laminar flow. Then you may use Nusselt number equal to 3.66. Okay, the thermal conductivity K for use in the Nusselt number relations should be evaluated at the bulk mean temperature. In laminar flow in a tube with constant surface temperature, both the heat transfer coefficient remains constant in the fully developed region. So we know that in my previous video, when we refer to the figure, so we know that for the entrance region, we have entrance region, hydrodynamically entrance region. One is hydrodynamically entrance region, and then we have another region for the fully developed region. And as we can try to revise back at point number 1, the region number 1, where we have the hydrodynamic entrance region, we have Nusselt number that is reduced as the x increases, and after it reached to some certain, after it reached to some certain point where the fully developed region starts, and it will remain constant throughout this region. Okay, so this is Nusselt number will be remain constant for a fully developed region, and it will reduce and it will change as the x coordinates increase in the hydrodynamic entrance region. So now for the laminar flow, we are focusing more on the fully developed fully developed laminar flow, where at this point, the fully developed laminar flow, the Nusselt number would be 3.66, constant throughout the X. If you have 10 meters length and then you have hydrodynamically fully developed region starts from 5 meter and another 5 meters would be 3.66, okay, because the Nusselt number would be constant. So what about the entrance region? So for the entrance region, we have another types of equation that can be used in order for you to determine what is the Nusselt number. So this slide, okay, current slide, is for developing laminar flow. Okay, so the entry region's laminar, so you may use these kinds of equation. Nusselt number is 3.66 plus 0.065 times with d over L Reynolds number times with Prandtl number over 1 plus 0.04 d over L Reynolds number times Prandtl number 2 over 3. So the average Nusselt number is larger at the entrance region. So and it approaches asymptotically to a fully developed value of 3.66. It means that in the entrance region, the value of the Nusselt number might be higher than 3.66. For example, we know that the value for the Nusselt number will be reduced as it approaches to this point where the fully developed region starts. So when the fully developed region starts, it will start to constant for the Nusselt number. So at this point, as we can see here, it will reduce, and at this point, the Nusselt number is 3.66, and it will remains constant after that. And before that, it might be different value with 3.66, maybe 37, 36, 35, and it will reduce up to 3.66. Okay, and that's why here states that, and it approach asymptotically to a fully developed value of 3.66. So after L is approaching to infinity, and that value and that region, when the region of the fully developed region starts, when fully developed region starts, and it will remain, or it will, the Nusselt number will be constant. Okay, when the difference between the surface and the fluid temperatures is large, so you can calculate the temperature difference between fluid and surface temperature. So you may use the entry region laminar equation, this, when the temperature difference is large. And then all properties are evaluated at the bulk mean temperature. So for this equation, and for this also for this equation, we will calculate, or we will try to find the properties at bulk mean temperature. Okay, and for the case of this equation, we can see that there will be a mu s. So here is mu s. Mu s is only properties evaluated at surface temperature. So you have to evaluate this at surface temperature. And for the other temperature properties, you may refer to bulk mean temperature. Okay, the average Nusselt number for the thermal entrance region of flow between isothermal parallel plates. So this is for parallel plates. So we are dealing here now is for the internal forced convection for a cylinder. So if you are calculating or try to find what is the Nusselt number for a parallel plate. So let's say we have this plate and then we have another plate here, then we have fluid inside. So this fluid can be considered as internal force convection or internal flow. Okay, internal force convection occurs here. Then you can use this Nusselt number equation in order to find what is the value of this Nusselt number. Okay, so this Nusselt number is can be used for the Reynolds number below than 2800. Okay, for turbulent flow in tubes. So now if you have a Reynolds number in a turbulent flow types, okay, you may use the Nusselt number here. The equation is 0.125 friction factor Reynolds number times with Prandtl number. Since we are not dealing with this friction factor, so we will not use this kinds of equation. So for the Reynolds number which is greater than 10,000, here is for fully developed turbulent flow equation. Okay, this equation is applied for fully developed turbulent flow, where the Reynolds number must be greater than 10,000. So you have to calculate what is the Reynolds number, and then if that Reynolds number is turbulent flow, it must to use this equation, you must your Reynolds number must be greater than 10,000. And this is called Bern equation. And after that, some modification has been made, and it comes up with the Ditters-Boyter equation. So you will use this equation in your calculation. So this equation is only for fully developed turbulent flow. So you may assume that the flow, when you calculate, you get 11,000, and you assume that that flow is actually fully developed turbulent flow. Then you may use this equation. So you have to remember that this equation will be used in your calculation to answer and to find what is the Nusselt number for your question. So let's see here. Nusselt number is equal to 0.023 Reynolds number times to the power of 0.8, Prandtl number to the power of n. So n here represent 0.4 for heating and 0.3 for cooling. So for at this point, you may I draw this figure. So you have a tube where the fluid flow inside of these tubes. Then how can you check whether that flow and this n is heating or cooling? So let's say you have Ti is equal to 30 degrees Celsius and T exit is 40 degrees Celsius. From here, you can see that the temperature inlet is much more lower than temperature exit. So these tubes are heating. So this is heating cases. So for this case, you will use n equal to 0.4. So for cooling process, so you may refer to the temperature inlet and temperature exit. So you have temperature inlet is 40 degrees Celsius, and then your exit temperature is 20 degrees Celsius. Then your Q is from in to out, from inside to outside, and your exit temperature is much more lower than inlet temperature. Therefore, this is the cooling process. So this is cooling. Therefore, you will use n equivalent to 0.3. Okay, so you must substitute this n with 0.4 or 0.3. How to know? you have to draw and check whether your exit temperature is much more greater than T inlet or your inlet temperature is greater than T exit. Okay. Again, when there is a large temperature difference between surface temperature and your fluid temperature, therefore you may use this equation in order for you to determine what is the Nusselt number. Here, all the properties will be evaluated at bulk mean temperature. For the only for mu s will be calculated at or evaluated at surface temperature. Okay, so in your calculation for fully developed turbulence flow, you will use this equation. Okay, this equation. So take note on this equation. So for liquid metals, so you will use this Nusselt number. So we have two different conditions there. If you have constant surface temperature, so the Nusselt number is 4.8 plus 0.0156 Reynolds number to the power of 0.85. Prandtl number surface 0.93. And then for liquid metals with the heat flux, constant heat flux, you may use this equation. Nusselt number 6.3 plus 0.0167 Reynolds number to the power of 0.85. Prandtl number surface 0.93. So that is for turbulent flow. Okay, for the turbulent flow, you have to assume fully developed turbulent flow. Now we go to flow through tube annulus. What is the tube annulus? I will not explain more. This is just surface of this annulus, tube annulus. You will calculate more on this part in the heat exchanger because you have concentric heat exchanger or double tube heat exchanger. Now for the annulus, so let's take a look at this figure. So you have tube inside tubes. So you have tube here and then you have another tubes outside that will wrap around the first tube. And the area in between those two tubes is what we call as annulus. Okay, in order for you to calculate what is the hydrodynamic diameter for the annulus, so we know that the importance of hydrodynamic diameter is in Reynolds number. So you will use this hydraulic diameter in your Reynolds number. So this hydraulic diameter, in order for you to find what is the Reynolds number for the annulus, you may change the dH not to di, but to d out minus di. So here you may change your Reynolds number to d out minus d in divided by kinematic viscosity. So this is the equation to find Reynolds number for annulus. Okay, for laminar flow, the convection coefficient for the inner and the outer surface are determined from. If you calculate this Reynolds number, then you get below than 2300. So you have two different types of Nusselt number. Now this is Nusselt number I and Nusselt number O, outer. So HIDH over K for the Nusselt number I, and Nusselt number out is HODH over K. So the difference between these two equations, you may find this Nusselt number in this figure. So table 8.4, where this table 8.4 shows you Nusselt number for laminar flow. Okay, so you will understand more on how to use this table when you learn chapter heat exchanger. Okay, but for now, you know that there is a case or there is a situation where we have tubes inside tube, and we call it and is as annulus.